Welcome to Math Science History. I'm Gabrielle Burchak, your host. There's a concept in physics called exponential decay. It describes how radioactive elements lose their energy over time, not all at once, but gradually, invisibly, half of what remains disappearing in every passing moment. Recognition, it turns out, has a half-life too. This is the story of Rosalind Franklin and the half-life and redistribution of her recognition. Rosalind Franklin never got to see what her work became. And this podcast is about not just how credit is given, but how it fades, how it gets redistributed, how the names we remember are sometimes the names that were louder, and how the quiet ones, the ones hunched over a diffractometer at 3 a.m, doing the actual work, can disappear from history before history even knows it has a debt to pay. In the basement of King's College London in 1952, Rosalind Franklin was doing something no one had done quite so precisely before. She was teaching X-rays to read the language of life. She was brilliant, methodical, and exacting, a quality many of her colleagues found intimidating. She didn't speculate. She did not build models from hunches. As Franklin herself put it, she said, "We are not going to speculate. We are going to let the spots on this photograph tell us what the structure is." The process was painstaking. Franklin suspended a DNA fiber, no thicker than a strand of hair, inside a micro camera she had modified herself, then bombarded it with X-rays for roughly 100 hours under carefully controlled humidity. She discovered that DNA existed in two forms, a dry A form and the wetter B form. Most colleagues focused on A. Franklin suspected B would be more revealing, and she was right. On May 2nd, 1952, she captured photo 51, the 51st image in the series. What emerged from the developer was a dark, haunting X shape against a gray background. To the trained eye, it was unambiguous. The lighter diamond shapes above, below, and on either side of the darkened X suggested the pattern of a double helix. From that single image, Franklin derived a radius of the molecule, a 10 nucleotide spacing per helical turn, the inward-facing bases, the outward-facing phosphates, and the two-stranded architecture of DNA. She had decoded the structure of heredity, and she hadn't yet published it. Before we get to what happened next, I'm going to take a quick pause on her technique because it's really remarkable. X-ray crystallography works on a beautiful paradox. You learn the shape of something invisible by studying the shadow it casts. When X-rays are aimed through a sample, they diffract in different directions depending on atomic locations, and scientists work backwards from those patterns to reconstruct the three-dimensional structure, like deducing someone's height from their shadow. Franklin calculated 10 base pairs per helical turn from the repeating units in her diffraction patterns. That number wasn't a guess, it was geometry extracted from light. The technique Franklin mastered in that London basement in 1952 remains foundational today. For example, during the COVID-19 pandemic, synchrotron X-ray crystallography was used almost immediately to solve the structures of key SARS-CoV-2 proteins involved in viral replication, including the main protease accelerating structure-based drug discovery. That's how we got our vaccines. The path to vaccines began even earlier than this. In 2017, researchers studying coronavirus spike proteins determined how to stabilize the spike in its perfusion shape. It's a structural insight that became a critical design element in the first mRNA COVID-19 vaccines. And in that sense, the mRNA vaccines that went into hundreds of millions of arms trace a direct scientific lineage back to the structural work exemplified by photo 51. Rosalind Franklin could not have known, of course. She just kept adjusting the humidity, exposing the fiber, and reading what the light told her. So here's the theft that was not spoke of. Franklin was preparing to leave King's College in early 1953 and would move on to Birkbeck College. In January of that year, James Watson visited King's College. While visiting, Maurice Wilkins showed Watson one of Franklin's X-ray diffraction images, photo 51, without Franklin's knowledge. Watson, who was already racing with Francis Crick to model DNA structure, recognized the helical signature immediately. He and Crick then used the critical measurements from photo 51 along with data from a confidential Medical Research Council report that also contained Franklin's findings to finalize their famous double helix model published in Nature in April 1953. Franklin was not acknowledged in the published paper. 3 papers appeared in Nature that day, one from Watson and Crick, one from Wilkins, and one co-authored by Franklin, were presented as parallel complementary work, but they were not equal contributions dressed in equal clothes. Franklin's data had seeded the model, her image had confirmed it, and yet the story that hardened into history positioned her as a supporting character in someone else's discovery. But the irony in her presence at Birkbeck is that she thrived there. She was doing important, recognized science in a place that genuinely valued her. We'll be right back after a quick word from my advertisers. Sadly, in 1956, she was diagnosed with ovarian cancer at the age of 37. 2 years later, she passed away, leaving a prominent legacy with her work. In 1962, Watson, Crick, and Wilkins shared the Nobel Prize in Physiology or Medicine. The Nobel is never awarded posthumously, which is a shame, because whether she would have been included remains one of science's most debated counterfactuals. What is not debatable is that she wasn't there, and that for decades she wasn't much mentioned either. It was Watson's 1968 memoir, The Double Helix, that paradoxically rescued her from obscurity by creating such an unflattering depiction of her that historians and scientists were provoked into re-examining the record. What they found was a woman who had not merely contributed to the discovery, but had independently derived many of its most critical conclusions. Notebooks from Franklin's own hand show that once she turned her attention fully to photo 51, she extracted every key piece of structural information the image contained. Researchers who have studied the period believe that, given more time, she would have arrived at the double helix on her own. The discovery of DNA structure is one of the most consequential moments in scientific history. The foundation of modern genetics, the sequencing of the human genome, the mRNA vaccines, and our entire understanding of what makes living things what they are. The advances in identifying and analyzing the genetic code based on Franklin's work have produced breakthroughs that have changed the trajectory of science. This pattern didn't die with her. It would be comfortable to believe Franklin's story belongs in another era. The data says otherwise. In a 2022 study in Nature, the same journal that printed Watson and Crick's paper found that women who work on research projects were 13% less likely to be named as authors on scientific articles and 59% less likely to be named on patents, even after thoroughly investing their time and efforts for the research. Additionally, the gap is sharpest early in careers. Only 15 in 100 female graduate students are ever named as an author, compared with 21 in 100 male students. As one lead researcher puts it, there were anecdotes like Franklin's, but now there is evidence, and the gap is strong, persistent, and independent of research field. The closest modern parallel belongs to Catalin Carrico. Throughout the 1990s, she struggled to convince funders of the potential mRNA as a therapeutic tool. She was demoted 4 times at the University of Pennsylvania. In 2005, her key paper was rejected by both Nature and Science as not novel enough. It was published in a smaller journal, which sat unnoticed for years. Then came COVID-19. In 2023, Kariko and Drew Weissman won the Nobel Prize in Physiology or Medicine 2 decades after the rejection, 4 years after their technology helped end a pandemic. She received recognition ultimately, but the delay, driven by years of skepticism and defunded research, cost countless lives when the pandemic arrived. What Franklin and Kariko share isn't simply that they were underestimated. It's that the mechanism of their erasure was entirely ordinary. No villain decided to steal credit. The system just ran its normal course. The photocopier was unlocked. The report was shared. The grant reviewers passed, and the editors declined. When we accumulate enough of these ordinary moments, we get a half-life. The same journal that once erased Franklin is now publishing the data that proves the pattern continues. That is progress of sorts, but measurement is not the same as remedy. Rosalind Franklin knew the shape of DNA from its shadow. We know the shape of this problem from its data. The question this podcast really asks is whether knowing is enough. In physics, exponential decay doesn't go on forever. Every element eventually reaches its stable form, the point where decay stops and what remains can no longer be diminished. The world is finally reading Franklin's record. A Chicago university was renamed in her honor, incorporating Photo 51 in its logo. I love that. The Royal Society issues a Rosalind Franklin Award annually. A film starring Natalie Portman entered production last year in 2025, and Aaron Klug, whom she mentored at Birkbeck, credited her directly in his 1982 Nobel lecture, saying she introduced him to the study of viruses and that he could claim no credit for that first subject. Her influence propagated forward, prize to prize, like a signal in a medium she could no longer inhabit. That is the deepest truth about exponential decay applied to recognition. The energy doesn't disappear, it transfers. Watson and Crick's names are in every textbook. The credit accrued, compounded, and calcified. And here is what exponential decay cannot account for: the stubborn persistence of the true record. Notebooks don't forget. Photographs don't lie. The X-shaped shadow on Photo 51 did not change when Watson walked into that room, or when Wilkins unlocked the filing cabinet, or when the Nobel Committee convened in Stockholm. It said what it had always said. Franklin's gravestone reads, quote, "Her work on viruses was of lasting benefit to mankind," unquote. They did not put DNA on it. Whether that was erasure has no clean answer. But the science, in her hands, in her basement, on her film, was never in doubt, and it still is not. Some things decay. Some things, it turns out, are stable from the very beginning. We just took 70 years to stop arguing about it. That said, let it be known that every half-life has an endpoint. Every decay curve flattens. The question is whether you are around to see it. Don't leave that to chance. Until next time, carpe diem. Thank you for listening to Math Science History. If you want the next episode as soon as it drops, just tap follow in your podcast app. Math Science History is brought to you by caffeine. Delicious, delightful, life-supporting caffeine. If you'd like to support the show, you can find the coffee cup link in our show notes or at mathsciencehistory.com. Just click on that coffee cup. Your donations don't really go to coffee, but they really do help cover production costs. The MSH theme is public domain from the late, great music composer and professor, Dr. Lloyd Rogers. All other music is public domain from Pixabay. Until next time, carpe diem.